Tuples 101. Basics. A tuple is an array of things. Our tuples will be an array of integers. We have positive integers, negative integers, and 0. And this is confined to basics. In the tuple above, 2, 4, 5, 7. The 7 is in the ones position, the 5 is in the tens position, the 4 is in the hundreds position, and the 2 is in the thousands position. The tuple has the integer equivalent to 2,457. In example 1, the tuple 4, 25. 25 is in the ones position and 4 is in the tens position. To convert this to an integer, we simply move the 2 in the 25 to the 4, added to the 4, that becomes 6. And so the tuple 4, 25 is converted to 65. In example 2, the tuple 3, 42, 93 is a 3 tuple, and it will be converted to an integer by moving the 9 in the 93 to the tens position and adding it to 42. So 9 and 42 is 51. The 5 is moved to the 3 in the 100 position, yielding 8. That's 3 plus 5. The final number is 813. When we convert tuples into integers, we usually work from the right to the left, and the desired form of the final tuple, before we convert it into an integer, would be have the leftmost integer can be more than one digit, but all the integers to the right of that are single digits. Now, the final form before conversion to an integer. We notice the tuple 65, 1, 2, 3, 4, 7, 2. 65 is in the leftmost position, so this one's okay. So we just simply remove the commas and make an integer 6512372, which is 6,512,372. Our next one, there's a negative 4, negative 1, negative 2, negative 3. You can pull the negative out. It's like factoring a negative. So it's negative 4,123. Now we look at the tuple, negative 256, negative 8, negative 7, and a 0. The multiple digit integer is in the leftmost position. We pull the negative out. It's minus 256,870. The next two tuples are going to indicate when the converted integer is positive or negative just by looking at the digits of the tuple. Notice, in this tuple, the next one, 1, negative 9, negative 4, 5, negative 7, negative 2. If they're single digits and the leftmost digit is positive, you will convert this to a positive integer. In the next example, the first leftmost digit is negative 1. It doesn't matter what the other single digits are, this will be a negative integer. And so in the next slide, we will learn how to turn these into the integers. Multiples of 10 can be added to integers in a tuple to yield positive single digits or 0. Multiples of 10, 10, 20, 30, 40, and so forth, and negative 10, negative 20, negative 30, and so forth. Also, multiples of 10 can be added to integers in a tuple to yield negative single digits or 0. We return to the tuple that was in the previous slide. 1, negative 9, negative 4, 5, negative 7, negative 2. We're going to work right to left. Now, to remove the negative 2, add 10. Then you will subtract 1 in the next column to the left. If you add 10 ones, you must take away 1 10. Our new tuple is 1, negative 9, negative 4, 5. Now we have negative 8 from negative 1 and negative 7. And 10 and negative 2 is 8. When we work from right to left, the entire tuple is changed to positive single digits or 0, except possibly the leftmost integer, which can have more than one digit. Now, the negative 2, we added 10, and that gives 8. But we got to take away 1 in the next column to the left. That's also a negative 8. We add 10, that's a blue 10. And then we subtract 1 in the next column to the left. So now, the negative 8 and 10, that's 2. And 5 and negative 1 is 4. So we go to the next integer, that's -4. We add 10, take away 1, so that gives us a 6. And -1 and -9, that's 10 that we add, and that will result in a 0. But when we add the purple 10, we got to take away 1, and that gives us 0. Now, in the final tuple, you don't need to write the first two zeros, but the 6428 form the integer 6,428. The tuple that starts off on the left with a -34 dominates the negativeness of the tuple, and this will turn to be a negative integer once we convert it. We will change every integer in the tuple except the -34 to a single digit negative integer or 0. We start with a +9, add a -10 to that 9, and then add 1 in the next column to the left. 9 and -10 is -1. 3 plus 1 is 4. We add another -10, that gives -6, and we add 1 in the next column to the left. 2 plus 1 is 3. Add a -10. That gives you a -7. We have to now add 1 in the next column to the left. -7 and plus 1, that is -6. It's negative. We don't have to do anything. Come to 18. We have to add a -20 and then add 2 in the next column to the left. 18 -20, that's a -2. -34 and plus 2 is -32. All the integers now in the tuple are negative. We factor the negative out, and you have left -3226761. That's -3,226,761. Now, some more tuples when converted to negative integers and positive integers. We look at the first one. -1 is in the hundreds position. The 9 and the next 9, they're in the 1 and the tens position. So this is like 99 and -100. That's -1. So in the next example, you got -1 and a bunch of 9s. If they're single digits and they're positive or negative, and the leftmost digit is a negative integer, and all the integers are single digits, it will be a negative integer. So in the example, -1, you got +2, -4, +5, a 0, and a -3. The -1 is in the leftmost position. It is a negative integer. The opposite is true if it's a positive integer in the leftmost position. So when we look at 1, -9, -9, that's -99 and 100. That is equal to the positive integer 1. We take the other example, 1, you got a bunch of -9s because they're single digits, and the last digit, the leftmost digit, is a +1. It is a positive integer. Mathematical operations: addition, subtraction, multiplication, and division. Add the ones integers, then the tens integers, then the hundreds integers, etc. to form a tuple. Then the tuple is converted into an integer. Our problem is 945 plus 892. We write the problem as tuples. We've got 945 and 892 in the first two rows. The vertical lines in the boxes form the place of the parentheses and the commas. Now, we're going to do add 5 and 2. That's 7. That's the ones integers. Now we do the tens integers. 4 and 9. That's 13. Add the hundreds integers. 9 and 8. That's 17. Bring the 7 down. The 13. Bring the 3 down. Move the 1 to the 17. Add it to the 17, and that gives 18. Our final number is 1837, which is 1,837. Another addition problem. In this one, we have 945 plus 92. 945 put on top. It really doesn't matter whether it's the top line or the second one. And the next number is 92. If you wanted to put a number in front of the 92, you could put 0, but we're not going to bother with it. So we add the ones integers, the tens integers, the hundred integers. So 5 and 2 is 7. 4 and 9 is 13. There is no integer below the 9, so we just bring the 9 down. Now, we'll bring the 7 down, 13, bring the 3 down, the 1 gets added to 9 to make 10, so our final answer is 1,037. A money problem. Suppose one has 4 drawers of money. They're represented by the 4 rows of numbers to the right. The first drawer is short 5 hundreds, has 2 tens, and 11 ones. Similar comments would apply to the other 3 drawers. How much money do you have? So what we will do is add the integers in the ones column, add the integers in the tens column, and add the integers in the hundreds column. When we go to the first column, the ones column, 5 and -6 is -1. Add that to 11, that's 10. 10 and 9 is 19. Let's go to the middle. Okay, 15 and 2 is 17. Take away 3, that's 14. 14 and 9 is 23. We go to the third column. I see 2 and 8, that's 10. Take away 5, that's 5. 5 and 4 is 9. So we have the tuple 9, 23, 19. Bring down the 9. Move the 1 to the 23, that makes 24. Move the 2 to the 9, that's 11. So the total amount of money is $1,149. The mathematical operation subtraction. In the problem immediately below, we have a 6 in the hundreds position, a 9 in the tens position, and a 7 in the ones position, and we are subtracting 345. We will change every subtraction into an addition problem. Here's how we do it. The negative sign is applied to the 3, 4, and 5. The negative sign then becomes a plus sign. So now we have changed it. So if we start with the rightmost integers, 7 and -5, 7 plus a -5 is 2, 9 plus a -4 is 5, and 6 plus a -3 is 3, and our final answer is 352. For this subtraction, we have 824 minus 351. We immediately change the second row. We apply the negative to 3, 5, and 1 and change the negative sign to a plus sign. So now we have, starting with the rightmost column, 4 plus a -1 is 3. 2 added to a -5 is -3. And 8 plus a -3 is 5. The tuple 5, -3, 3. The 5 is in the leftmost column. It is a positive integer. The -3 and 3 are single digits. So the tuple 5, -3, 3 is a positive integer. The -3, we add a 10 to this and take away 1 in the next column to the left. Our final tuple is 3. -3 and 10 is 7. 5 and -1 is 4. And we have 473 as our answer. In this problem, we have 4 in the hundreds position, -11 in the tens position, and 2 in the ones position. We are taking away 1 in the hundreds position, 4 in the tens position, and -7 in the ones position. Immediately change the second row with the signs. The negative sign becomes a plus sign. 1 becomes -1. 4 becomes -4. -7 becomes 7. Now we will add these numbers up. 2 plus 7 is 9. -11 plus a -4 is -15. And 4 plus a -1 is 3. 3, -15, 9 is a positive integer. So we must add 20 to the -15. And since we've added 20, we must take away -2 in the next column to the left. And our final tuple will be 3 plus a -2 is 1. -15 plus 20 is 5, and we have the 9. Our final answer is 159. In this problem, we have 451,827 minus 123,947. Apply the negative to each integer in the second row. That becomes now -1, -2, -3, -9, -4, -7. Now we will add, starting on the right, 7 and a -7 is 0. 2 and a -4 is -2. 8 added to -9 is -1. 1 added to -3 is -2. 5 added to -2 is 3. 4 added to -1 is 3. Starting on our right, we have the 0. Don't have to do anything. The -2, we must add 10. Take away 1. Those are in red. Now we see that we have -1 and -1, that's -2. Add 10, take away 1 in the next column to the left, they're in blue. Now we have -2, -1, add 10, take away 1 in the next column to the left. We can now get our final answer. It doesn't matter whether you go left to right or right to left. We will start on the right, bring down the 0. We have an 8, and then -2 and 10, that's another 8. -3 and 10, that's 7. 3 and -1, that's 2. And a 3. Our final answer is 327,880. The mathematical operation multiplication. We start off with 79 times 4. We do 4 times 9, 36. 4 times 7, 28. Bring the 6 down. The 3 gets added to the 28 to make 31. Final answer is 316. This multiplication, 49368 times 4. We do 4 times each digit. 4 times 8, 32. 4 times 6, 24. 4 times 3, 12. 4 times 9, 36. 4 times 4, 16. The tuple, 16, 36, 12, 24, 32, will now be turned into an integer. Start on your right. Bring the 2 down. The 3 of the 32 gets added to the 24 to be 27. The 7 comes down. The 2 gets added to the 12 to be 14. The 1 gets added to 36 to be 37. The 7 comes down. The 3 gets added to 16 to be 19. Final answer, 197,472. Now, a 2-digit number times a 2-digit number, 37 times 48. We'll do 8 times the 3 and the 7. 8 times 7, 56. 8 times 3, 24. We slide over to the 4. It's really 40. So you see a red 0. 4 times 7, 28. 4 times 3, 12. Now we'll add these numbers up. 56 and 0, 56, 24 and 28 is 52. And we have the 12. Now we're going to turn 12, 52, 56, that tuple, into an integer. The 6 comes down. The 5 gets added to 52 to be 57. 7 comes down. The 5 gets added to the 12 to be 17. And we have 1,776 as our final answer. In this multiplication, we have 6 and a -3 on the top line, and it's multiplied by 2 in the tens position and a -8 in the ones position. We'll keep the numbers as they are. -8 times -3, 24. -8 times 6, -48. Now we will put a 0 under the 24. 2 times -3, -6. 2 times 6 is 12. Add these numbers up. 24, 0, 24. -48, -6, -54, and a 12. Okay, we're going to turn this into an integer. We will add 60 to the 54, and then we will subtract 6 in the next column to the left. Now, our next tuple is 24, 6, 6. We will now turn this into an integer. The 4 comes down. The 2 gets added to the 6 to be 8, and we have the other 6. 684 is our final answer. 6, -3 as integers is 57. 2, -8 is 12. 57 times 12 is 684. In this multiplication, we have 49 times 758 on the left. On the right, we have 758 times 49. Now, on the left, 8 times 9 is 72. 8 times 4 is 32. Then we come to the 5, which is really 50. We add a 0. 5 times 9 is 45. 5 times 4 is 20. We get to the 7. It's really 700. We add 2 zeros. 7 times 9 is 63. 7 times 4 is 28. We will add these numbers up. 7200 is 72. 32, 45, 0 is 77. 20 and 63 is 83. And we have the 28. We now change this into an integer. The 2 comes down. The 7 gets added to 77. That's 84. The 4 gets down. Move the 8 to the 83. That's 91. The 1 comes down. The 9 gets added to 28. That's 37. So our final answer is 37,142. Now, on the right, we have 758 times 49. We'll do 9 times 8, 5, and 7. That's where the 72, 45, and 63 are. When we come to the 4, it's really 40. We put a 0, and then we do 4 times 8, 5, and 7. That's the 28, 20, and 32. And we add them up, we get the 72, 77, 83, 28 as we had on the left. And then we turn it into an integer, and we still have 37,142. You might find putting the longer integer, the one with 3 digits, on top, then you have more digits on the rows than doing it vertically. We had 3 rows. So if we have the smaller integer on top, we usually have more rows, and if we put the larger integer on top, we have less rows but more integers on the horizontal rows. The mathematical operation division. We will first do an example of traditional division. Here's how it works. We're dividing 6 into 5, 8, 9, 3, 6, 4, 2. 6 does not go into 5. 6 does go into 58. 9 times 6 is 54. We will subtract the 54 from the 58. So we're applying the negative 5 to the 5. That gives us 0. That's what we wanted. Gets rid of the first place. We apply negative 4 added to 8. That's 4. And we bring down the 9. Now 6 goes into 49 8 times. And so 8 times 6 is 48. We subtract the 48 from 49. That's 1. We bring down the 3. 6 goes into 13 2 times. That's 12. Subtract the 12 from the 13. That's 1. Bring down the 6. 6 goes into 16 2 times. That's 12. 16 minus the 12 is 4. Bring down the 4. How many 6's go into 44? 7. 7 times 6 is 42. Subtract 42 from 44. You get 2. Bring the 2 down. 6 goes into 22 3 times. That's 18. You take away 18 from 22. You get 4, which is called the remainder. 6 is called the divisor. 5, 8, 9, 3, 6, 4, 2 is called the dividend. The answer, 982273, is called the quotient. And from the numbers that are there, 6 times the quotient plus the remainder equals the dividend. This is a shorter way of traditional division, and this is a commonly known method. It doesn't take as much space. Now, we do 6 goes into 58 9 times. That's 54. 58 minus 54 is 4. Move the 4 next to the 9, which is a dividend digit. 6 goes into 49 8 times. 6 times 8 is 48. You subtract 48 from 49, you got 1. Move that 1 next to the 3. Now 6 goes into 13 2 times. That's 12. You got a remainder of 1. Move that next to the 6. 6 goes into 16 2 times. That's 12. You got a remainder of 4. Move that next to the other 4. How many 6's go into 44? 7. That's 42. You got a remainder of 2. Move the 2 next to the other 2. 6 goes into 22. 3 times, that's 18. You got a remainder of 4. This is a much easier way of doing single-digit division. Okay, our division now will be done with tuples. The 6 is going to go into 58 9 times. That's 54. The remainder is 4. Then we go 6 into 9. That goes 1 time. And the remainder is 3. 6 doesn't go into 3. 6 goes into 36 6 times. And that's 36. The remainder is 0. But write 0, 0. And 6 goes into 42 7 times. That's 42. And the remainder is 0, 0. So after the first set of quotient digits, the remainders are collected in one row, 4, 3, 0, 0, 0, 0. Now we start over again. How many 6's go into 4? None. How many 6's go into 43? 7. That 7 is in red. 7 times 6 is 42. The remainder is 1. And we just bring the other zeros down. Now we go 6 goes into 10 1 time. That's in blue. And 10 minus 6, that's 4. Bring the 0 down. 6 goes into 40 6 times. That's in green. 6 times 6 is 36. The remainder is 4. Bring down the 0. 6 goes into 40 6 times. That one's in black. That's 36. The remainder is 4. Bring that down the 0. 6 goes into 40. This one is in red. 6 times, that's 36, and the remainder is 4. Now, the quotient digits, we have 6 and 7 in the rightmost row of quotient digits, then 6 and 6, 1, 7 and 1, and 9. So 6 and 6, that's 13. The 1 goes next door to the 6, that's 7. Okay, 6 and 6 is 12. The 1 goes next door to the 1, that's another 2. And then we have 7 and 1 is 8, and we have a 9, and our quotient is 982273. We will now have some examples with 2-digit division and 3-digit divisors. In this division, we're dividing 21 into 5, 8, 9, 3, 6, 4, 2. 25 is a 2-digit divisor. 25 will go into a 2-digit number and a 3-digit number, possibly in this example. 25 goes into 58 2 times. That's 50. Subtract 50 from 58. That's 8. Go to your next 2-digit number. 25 goes into 93 3 times. 75. Subtract 75 from 93. That's 18. 25 goes into 64 2 times. That's 50. Subtract 50 from 64. That's 14. Bring down the 2. Our new dividend digits are 81, 81, 42. Our next set of quotient digits will be in red. How many 25s go into 81? 3. 75. Okay, 81 minus 75 is 6. Into the next 81. 25 goes into 81 3 times. That's 75. The remainder is 6, but write 0, 6. How many 25s go into 42? 1. So 42 minus 25 is 17. Our new dividend digits are 60, 617, and our next set of quotient digits will be in blue. So the question is, how many 25s go into 62? That's 50. Subtract 50 from 60. That's 10. Go to your 61. How many 25s go into 61? 2. That's 50. And you subtract 50 from 61, you get 11. Bring down the 7. Okay, now the 25 does not go into 10. That's a 2-digit number. But 25 goes into the 3-digit number 101 4 times. So 4 times 25 is 100. That's in green. Subtract 100 from 101. That's 1. Okay, 25 does not go into 17. Bring the 17 down. Now, 25 does not go into 11, but 25 goes into the 3-digit number 117 4 times, which is in a black quotient digit. And we subtract, we get a remainder of 17. We go up to our quotient digits. 1 plus 4 is 5. 2 plus 2 is 4. 4 plus 3 is 7. 2 plus 3 is 5. Bring the 3 up, bring the 2 up. Our quotient is 2, 3, 5, 7, 4, 5, and the remainder is 17. In this division, we're dividing by 17. Now, the previous division was, the divisor was 25. It's pretty easy to do 2 times 25, 3 times 25, 4 times 25. But if you don't know your 17 table, 2 through 9, you might want to write one down like I've done on the left. That will help us in the division. Now, how many 17s go into 58? 3. Can't be 4. 4 17s is 68. That's bigger than 58. So we use 3. 3 times 17 is 51. You subtract 51 from 58, you get 7. Now we move over. How many 17s go into 93? And we see from the table it's 5, and that's 85. You subtract, you get 0, 8. And how many 17s go into 64? Well, we look at our table. If we use 4, that's 68. That's too big, so we got to use 3. 3 times 17, that's 51. We subtract the 51 from 64, you get 13. Bring your 2 down. These are the new dividend digits. Okay, now the quotient digits will be now in red. So we ask the question, how many 17s go into 70? That'd be 4. 4 times 17 is 68. We get a remainder of 2. How many 17s go into 81? That would be 4 again. Get a remainder of 13. Then we ask how many 17s go into 32? Only 1. At 17, get a remainder of 15. 15 is less than 17, so it couldn't have been 2. Okay, so we now have our new dividend digits, 2, 1, 3, 1, 5, and the new quotient digits will be in blue. How many 17s go into 21? That's easy. 17. We subtract, we get 4. How many 17s go into 31? That's 1 again. That's 17. The remainder is 14. Okay, we don't do 17 to 5. We bring the 5 straight down. So now we ask the question, how many 17s go into 41? That's 2. That's in green in the quotient digit. We subtract, we get 7. And how many 17s go into 45? It's 2 again. That's 34. And get a remainder of 11. So now in black, the quotient digit, how many 17s go into 71? 4. Okay, 4 times 17, 68. We subtract, we get 3. 17 doesn't go into 1. We bring the 1 down. Now we ask how many 17s go into 31. That's the 1. That's way up there in red. And 31 minus 17 is 14 is our remainder. Our new quotient, we add up the tuples. So starting on the right, 1, 2, 1, that's 4. 4, 1, and 3, that's 8. 2 and 4 is 6. 1 and 5 is 6. Bring up the 4, bring up the 3. So we got for the quotient 3, 4, 6, 6, 8, 4, and a remainder of 14. In this division, we're dividing 123 into 5, 8, 9, 3, 6, 4, 2. Worked out a little table to the left, 123 times 2 times 3 all the way down to 9. So when we start off, 123 is going into a 3-digit number. 5, 8, 9 goes in 4 times, that's 492, and 123 goes in 364. 2 times, that's 246. We do the subtractions, we got 97, we got 118, bring down the 2. Then we say how many 123 is going in 971, 7, and that's 861. Do the subtraction, get 110. And how many 123 is going to 182? That's 1, that's 123, and we subtract with 059. Okay, then we ask how many 123 is going to 1100. This dividend digit will be in blue, the quotient digit will be in blue, and it's 8, that's 984. We do the subtraction, get 116, bring down the 59. Now 123 doesn't go into 116, it'll go into the 4-digit number 1165. Going 9 times, that's 1107. Do the subtraction, get 58. Bring down the 9. How many 123 is going to 589? That's 4, so that's 492. We subtract and get a remainder of 97. Now we do the quotient digits. We add 1 and 4, that's 5. 9 and 2, that's 11. It's the 1 on the top next to the 5. We move the 1 to the blue 8, that makes 9. Bring up the 7, bring up the 4, so the quotient is 47,915 with a remainder of 97. In this division, our original divisor is 55,673. We're going to form a modified divisor. We take the leftmost 2 digits, 55, and then follow that with 3 zeros replacing the 673. The 673 is written under the 55,000. For each quotient digit, we will have 2 subtractions. So our first task is how many 55,000s going to 58989? 1. We subtract 55,000 from that, and we get 3,989. Now we're going to do 1 times 673. Subtract that from 3989, you get 3316. Bring down the 4. 55,000 does not go into 33,164. Bring down the 9. Now, how many 55,000s go into 331649? 6. 6 times 55,000 is 330000. We perform our subtraction, we get 1649. But now we got to take care of the 6 times the 673. That's 4,038, and you subtract, you get a negative remainder, 2389. You can't get negative remainders and keep going. We go up to the 6, cross through it, and you reduce it by 1, and that's a 5, and that's seen at the top of the quotient digits. To fix everything up, by crossing through the 6 and putting a 5, we must add the original divisor, 55673, to the negative remainder, and we get 53284. Bring down the 2. So now we're back in order, and how many 55,000s go into 5328429? 9. That's 495000. We perform the subtraction, 37842. We still got to do now 9 times 673. That's 6,057. And we get the remainder of 31,785. We go up to the top. Our quotient is 9. The 6 was replaced with a 5. We have a 0 and a 1. So 1,059 with a remainder of 31,785. In this division, we're still dividing by 55,673. But we're going into 189899492. Now, 55,000 does not go into 18989. but 55,000 goes into 189894. So instead of starting the 5th digit over, we have to start in the 6th digit over for the first quotient digit. Now 3 times 55,000 is 165,000. We subtract, we get 24894. Now we got to do 3 times 673, that's 2019. Subtract that, and our new dividend is 22875. Bring down the 9. And we see that 4 55,000s go into 228759. So we'll go subtract from that 220000. We get 8759. And we also now have to subtract 4 times 673. That's 2692. And we get 6067. Bring down the 2. Only 1 55,000 goes into 672. We get a remainder of 5672. And now we got to do 1 times 673. Subtract that. And we get a final remainder of 4,999. And the quotient is 341. In this division problem on the left, the person divides 3 into 18, and they get a quotient digit of 5. But 3 times 5 is 15, and 18 minus 15 is 3. The remainder is supposed to be less than 3, 0, 1, and 2, but that's okay. We bring down the 9, and the person says, well, 3 goes into 39 13 times, and 3 times 13 is 39. You subtract, get a remainder of 0. But we're not supposed to have quotient numbers that are more than 1 digit, and 13 is 2 digits. However, our answer is 5, 13. You move the 1 to the 5, that's 6, 3, which is 63 is our quotient. Now, in the example on the right, 3 goes in 18, the person does 5 again, that's 15. They subtract, they get 3, and they say, oh, that can't be right, and 3 goes into 3. One time, that goes above the 5, and get a remainder of 0. Bring down the 9. 3 goes into 9 3 times, and 9 minus 9 is 0. You get it for the remainder. Now we look at the top. 5 plus 1 is 6, and move the 3 up, and so our remainder again is 63. What we strive for is when we divide, is that the remainder is less than the divisor, and the quotient digits are single digits. So we don't want 2-digit numbers or 3-digit numbers as quotient numbers. We want single digits. These are just a few comments. By the way, you might note that when we got negative numbers, when we did the secondary subtraction, when we were dividing 3-digit numbers into numbers, we then had to add the entire divisor to fix the problem up. So in these problems, they're not wrong, they just don't go by the standard rules. If we're using tuples, they will fix themselves up. Principia Tuples is my first book on tuples. In the first chapter, I show addition, subtraction, multiplication, and division by my new methods. Then second chapter starts with tuple definitions, what a tuple is, show basic multiplication, addition and subtraction, more multiplication. Then we proceed with polynomials as tuples, and later on we do polynomial values, including division. The division method is very simple, and it is much easier than synthetic division. Tuple division is much cleaner. We also show factoring with tuples, much easier than doing it with x's. Show the quadratic formula. We do third degree and higher factoring, and it's relatively easy with tuples. Then we show square roots and cube roots, how to use a current answer and go one more digit. And we also show base 2 with tuples, a much simpler method than what is commonly used. So if you do the base 2 with tuples, it's much easier. Then we do number tuples into integers, and the final chapter on tuples is the box method for multiplication. Once you learn the box method, it is very easy to do like a 3-digit number times a 3-digit number, a 5-digit number times a 5-digit number, or a 5-digit number times a 6-digit number. Much, much easier. The third chapter is a prime sieve, which shows you how to determine primes in a very simple manner. Tuples 2 is my second book on tuples. This is designed for youngsters to learn how to add, subtract, multiply, and divide using tuples. First, start off with tuples and integers, how to change tuples into integers and integers into tuples. We have basic subtraction and negatives, and then we have tuples, how to add, subtract, and multiply, and then we do some addition exercises with very detailed answers. Then we have a subtraction example, have multiplication examples with a lot of exercises and detailed answers, and then we also include the multiplication box method. So if we're doing 3-digit numbers times 3-digit numbers, is a very easy method to apply. Also for 4-digit numbers times 4-digit, 5-digit times 6-digit numbers, and so forth. There are a lot of division problems, and in this particular approach, we learn how to take a 5-digit divisor and turn it into a 2-digit divisor, and then follow it with zeros. We also learn how to change a divisor that maybe starts with 83 and turn it into a divisor that starts with a 1. Then we complete the square with tuples with some examples and exercises. We have a special example on completing the square with a 4-tuple and a special example completing the cube with a 4-tuple. There are many exercises with detailed answers throughout the book. Tuplematics is my third book on tuples. We start off with completing the square, completing the cube, and more completing the square and completing the cube, completing the 4th power and more completing the cube, and completing the 5th power. So these are like number puzzles. Then we do powers of integers, and these are like number puzzles. Then we start off with something that is truly amazing, tuples and modulus, and it is a simple way to divide integers into other integers and find the remainder. And then we have tuples and division. This is a crazy cool method for division. It is slick, and once you learn it, it makes dividing simple. So you can learn how to divide a 4-digit number into a 12-digit number very easily. The last chapter has nothing to do with tuples. It's a theorem, a special theorem on the sum of integers and the sum of squares of integers. What it basically says is this: if you pick any integer out that's greater than or equal to 3, say 10, you can find 2 sets of positive integers, that there are no integers that are common to both sets. All the integers in each set are distinct, and if you take their sums, the sums of the integers in both sets will equal, and the sums of their squares of the integers will be equal. But it doesn't stop there. The number of such pairs of sets is actually infinite, and that's for every positive integer greater than or equal to 3. The books, Concept Your Tuples, Tuples 2, Tuplematics, they're published with Amazon, and you can find them on www.amazon.com. Each book is $9.99. They're only in electronic form. There is no paper version. So if you buy one of these books, the idea is that you copy the problem down on paper, work it out, and then see if you got the right answer that's displayed in the book.